So, good morning, everyone. Welcome to this webinar from the Energy Transmission Competence Hub, or Etch. This webinar is one of a series of webinars where we share our research and have discussion on our research topics. With Etch, the Energy Transition Competence Hub, we're building a hub of knowledge and research, basically solving the energy transitions, the key challenges of the energy transition together with our partners around the world. So our presenters today are part of Etch and also K11, that's the University of Leuven in Belgium. And within Etch, we have 4 key research lines solving these key energy transition challenges. So we look into control interactions, planning and operation, cable-dominated systems, and also protection of future power systems. So the webinar today is part of our protection of future power systems roadmap. And within our protection team, we work on topics related to the design and application of protection systems in HVDC grids and also in converter-dominated AC systems. So we have a wide range of work relating to HVDC protection design, implementation, and testing for HVDC grids. Also experience with digital substations and the relevant control systems from HVDC. But this webinar is focused more on the AC transmission side and thinking about how what the impact of HVDC converters and converter-dominated systems is on existing and future AC protection systems. So today, Xiaoxiao will present, and she'll present and looking at basically the impact of HVDC converters on AC protection, some of the methods by which we can actually analyze and evaluate the challenges foreseen in future converter-dominated systems, and some outlook for the future and some key takeaways. So the format of this will be that there'll be a presentation, I think half an hour or 40 minutes, and then there'll be a question and answer session afterwards. So please drop questions into the Q&A, and then we'll try and answer as many as possible after the presentation. So thanks a lot for joining. Xiaoxiao, maybe you can share your screen and start the presentation.
Okay, I will share my screen now. Yeah, can you see my slides? Okay, great. Hello, everyone. My name is Xiaoxiao Liu. I'm a PhD student based on K11 and Etch, and also my PhD project is a global partnership collaborating between K11 and the University of Edinburgh. And today I'm going to talk about the AC fault response in this changing power system. And the grid is becoming more converter dominated, as we all know. And this means the AC faults are no longer as straightforward as they were with synchronous generators. With so many parameters in the converter control and so many stakeholders, TSOs, vendors, protection and control engineers, each they sees only part of the picture of the AC fault. That can lead to some misunderstandings and suboptimal system performance. So in this presentation, we will look at the challenges different stakeholders face and how we can use sensitivity analysis to see what really matters for different stakeholders. And now I will start my presentation. And first, maybe I turn on the laser. Yeah. To face the challenges of the climate change, more and more renewable energy are integrated into the traditional power system. Our power system is having a top-down change from the stable centralized generation and the clear AC transmission to a complex mix of wind, solar storage, and offshore connections, from the synchronous generator-dominated system to a converter-dominated system. This will make the AC fault currents less predictable and more depend on the converter controls. In traditional power system dominated by the synchronous generators, when there is a fault happen at the AC system, because of the inertia of the synchronous generator, the terminal voltage can be considered as unchanged after the AC fault, which will bring high fault currents on the AC fault transmission lines. And this dynamic is well understood and also lead to straightforward protection design. We can use the equivalent simplified model and implement symmetrical component-based fault analysis. Then we can predict the fault current or impedance, fault impedance characteristics. Using this, the protection design and the threshold setting up is largely based on this, and it's very straightforward. But in the converter-dominated system, it has changed the whole game. In this presentation, we will just focus on the transmission system. This is largely using HVDC now, and how HVDC change the AC fault is quite important for the future protection design. And because the HVDC converters rely on fast and software-driven control instead of the natural physical inertia, for example, so the fault current behavior is largely dominated by the control. So if we change the converter control strategy from without voltage support to with voltage support, the gray side current will have a very largely change. And if we change the current injection rate from a fast injection to a slow injection, we can also see very different fault current dynamics. So that means the AC fault characteristics is basically dominated by the control. And also it's quite unpredictable. For example, here is the comparison between the fast current injection and the slow current injection under different fault scenarios. And we can see that the maximum current are distributed very differently. And besides this, we don't have really standard models to analyze the AC fault. So we really need a very straightforward way to understand the AC fault dynamics in converter-dominated power systems. But the AC fault dynamic is not the converters or the controls only responsibility. Here you can see the power system really is a shared responsibility. We have over 11 million kilometer transmission lines in Europe alone, and around 40 TSOs to more than 2,000 DSOs, and at least 4 major HVDC and converter vendors globally. And behind this, we have a lot of control engineers and protection engineers. So every part of the chain depends on others. And if we want to understand how faults and the controls interact, we cannot look at it in isolation. But to make sure all these parts actually work together, from converter controls to transmission to local distribution, we rely on grid codes. And grid codes under AC fault, grid codes define the technical rules for what's required during faults, how converters should inject the current, and how voltage should be supported, and how different assets stay connected. And the European grid codes started from 2013, and NSOE and SAER started drafted the European grid codes, and the regulation officially enacts in 2016. And it's already required the converter to have a low voltage rise-through, high voltage rise-through, and a reactive current injection. And among 2018 and 2021, different countries in Europe started to implement the grid codes based on their nation power system requirements. And right now, the grid codes are still changing to adapt to the new power system and adapt to the grid forming. So this actually brings a lot of challenges to different stakeholders. For TSO, they need to understand if the grid code is enough for today and what we still need to change. For vendors, they need to know how we can actually make sure that the converter design can comply with the grid code. Therefore, we need to think from different perspectives. And for the TSOs, the responsibility is basically they need to maintain the stability and the reliability of the transmission network and the balance the supply and demand, and ensure that the flows smoothly through the network. And so they actually need to know in this converter-dominated system, they need to know how the converter control behaves under faults and what kind of current are expected, and which converter parameters will affect the grid code compliance, and whether the grid codes are still valid in nowadays. And during the AC faults, the grid codes usually will require the converter to have rise-through capability, reactive current injection, and active power recovery. And here we can see how different countries set slightly different voltage recovery profiles, like Germany, Spain, Denmark. So a converter must remain connected or chip based on how these ratios are defined. And on the right, here is the current injection, and it basically when the current drops to a certain level, it needs to inject reactive current. And there is already one project analyze which part of the grid codes are still remain unspecific. For example, here we can see the current injection droop K and the current characteristics rise time and the settling time and the priority between active and reactive current during the faults are still not really specifically defined in the grid codes, and there are so many freedom, let's say, and we also need to know which control parameters are related to these characteristics. So sensitivity analysis can give us some guideline on which parameters matter. And for the vendors, their responsibility is to design converters that are robust and flexible and to communicate clearly how they behave in the system with other stakeholders, especially with TSOs, because they are the customers. But they also need to make sure they cannot really expose their core intellectual property. So they need to balance the openness for the system stability with the protecting what's inside the black box model. So they also need to know under AC fault which internal parameters influence the most, and how to design the converter and to make sure it's comply with the grid codes. And they also need to communicate the limitations and the flexibility to the customers. And the sensitivity analysis can tell the vendors under the AC fault if the customer needs this parameters, this control blocks needs to be open to the customers, and it can reduce the time, the engineer hours for the customers and for them to communicate and to upgrade. And for control engineers, it's quite straightforward because control engineers need to design the control strategies to make sure the fault rise root capability work across different grades and different scenarios. And but small parameter changes can cause large behavior shifts. So we need to know also which parameter really matter under the fault conditions and how to tune the control parameters to make sure the system remains stable under different scenarios. And for the protection engineer, because now the AC fault characteristics is largely depend on the control system. So we need to know under this new converter domain system if the original distance protection still work, and if it's not work, what caused it not work, and if we can find a solution to solve this problem. And if we can still use the traditional protection fault detection algorithms, or we have to make sure to make some radical change on the protection system. And the purpose of this study is actually also build some sort of bridge between the control and the protection. Under this way, we can understand them better and try to develop a more coordinated control and protection system for the future. And basically, the whole problem now is like in the converter control, we have too many parameters, but we don't really know, at least from different stakeholders, they don't really know that which control parameters are the most important one. And also every stakeholders see things from different lens. So we really need to make this process more simplified. And we basically need to see from a system level lens and to know which parameters are most important for different stakeholders, and make it more straightforward. And for doing this, sensitivity analysis can help us because it can identify the most important parameters and just to choose the most important parameters to this bunch of parameters and can basically simplify the whole analysis. And for different stakeholders, they just need to focus on this small group of prioritized parameter sets, and then they can understand the system better and also without understand every part of the control system. And the sensitivity analysis here we are using is called elementary effects. So basically, for elementary effects, first we need to define the input parameters. As I said, because the control is dominated the AC photo response, so the control parameters are the researched input parameters. Basically, we analyze that when the control parameters changes, how the AC side photo responds to those change. If we have K control parameters that we are interested, then the input parameter grade will be K dimension. For example, here is a two-parameter system, so it is a two-dimension input grid, and here is a three-parameter system, and it's three-dimension grid. And each input parameter has P levels. Here it has 4 levels for each parameter. And in control system, for each control parameter, we can tune it differently, but we have a range that can make sure this system works stable. So first we need to define the range of the input parameters and divide those parameters into different ranges. And for the output, as I said, that we are analyzing the impact on the AC fault. So the output will be defined to reflect the AC fault characteristics. But for different stakeholders, they look at different outputs. For example, the TSOs will look at the injected current characteristics, and the protection will look at the output related to the protection performance. The third one is the elementary effects. Basically, it's looking at when we change a parameter X and how much difference it will cost on the output Y. And if there is one parameter that we just change, we just have a small change of delta, but it causes a very different output, then the elementary effect will be also very large. Because we have this big input parameter space, so what we are doing is like we randomly change the input parameters in this space, and every time we just change one parameter, and we will calculate the elementary effects when we change that one parameter, and we will have a randomly scan in this big space and calculate all the elementary effects for every step. So after one time scanning, we will get a lot of elementary effects for each parameter. Then we calculate the average value of the elementary effects and the standard deviation. The average value will tell us if the sensitivity of that parameter is large. If this value is very large, that means a small change on this parameter will cause a big change on the output. And the standard deviation will tell us that if it's large, that means even though we have a same change on the parameter, but because it's changed from the different place, so it might cause different impact on the output. So this part, this parameter sensitivity effect might be nonlinear and might have some interactions with other parameters. And this is basically the main concepts of this method. And here I present a very simple results of this method. Basically, I choose like 5 parameters in the converter control and implement a 3-phase fault and find out which parameters are more sensitive to the three-phase fault current characteristics. Basically, the x-axis will be the mean value of the elementary effects. It will from small to large. It means that the parameter is less sensitive to more sensitive. And the y-axis is the standard deviation. From small to large, it means the effect will from less nonlinear to more nonlinear and less interactive with other parameters to more interactive with other parameters. And if we have some parameters located here with very small mean value and small standard deviation, which means they have very low impacts. So during analysis, we can ignore their effects because they just don't have enough impacts on output. So we can simplify the analysis. And if we have some parameter located here, it has very high mean value, but not really high standard deviation, which means it has high impact, but not really interaction with other factors. And we also might find some parameters located here. They have high impacts and interactions with each other, and their impacts will be nonlinear. And this will help us to understand the results I present later. The research objective in this presentation is basically MMC, because MMC control system is relatively complicated, and it has different levels of control blocks control system. And for example, it has power active reactive power control and DC voltage control, and it also has energy balancing control, including the total energy balancing and the horizontal and vertical balancing. And this will calculate the current reference, and the current reference will be transferred to the current control block. Then it will get the arm voltage reference and to the low level control, and it will generate some firing signals to the MMC itself. For the outer loop controller, it can actually be grid following or grid forming. And here in this presentation, I will just focus on the grid following. And for grid forming, there are also very kind of different AC fault characteristics. And for the internal arm energy balancing, when we analyze AC side faults, most of the research, if they are not look at the converter internal fault characteristics, they don't really talk about the energy balancing. But here I include it because I think it's not really. We cannot just ignore some control blocks because we are not looking at the internal. Probably it will also have some impacts on the external, and later I will show some proof. The control system in my simulation is shown in this figure. And basically, it's basically the same as the other blocks, and they just in more detail. After AC fault happens, the control system will switch to the fault current injection, and the fault current injection is defined by these two parameters. K FCI is the droop of fault current injection. That band FCI is defined when we are going to inject the fault current, and also with energy balancing, including the total energy control and the horizontal and the vertical energy control. And in this energy control, I will focus on the proportional gain of total energy control, horizontal vertical balancing control, and also energy control factor, KTE. This defines how much power from the AC side is used for the total energy balancing. If this value is 0, that means we are all using the DC side power to balance the total energy of MMC. If this value equals to 1, that means we are all using the AC side power. Except this PLL is also one influential factor during the AC fault, and I use the proportional gain with the PLL to see the impact. And the outer loop, because in MMC HVDC system, if one part of the DC side MMC is has AC fault, then the other side needs to take over the DC voltage control. So I include the DC voltage control parameters as as analyzing abstract 2. And here is the table of the input parameter and also the parameter domain we selected. As I said, first we need to define the parameter domain, and then we change the parameter in the defined parameter domain to see how the change affected the output. And this definition of the parameter domain has to make sure the system is actually stable before the fault happens, and it can also lead to stable fault recovery. Yeah, and it has to make sure that it meets with the dependency requirements between the outer loop and the inner loop. For example, the outer loop has to be at least 10 times slower than the inner loop. And the scenario in this presentation is just the single phase A to ground fault at the gray side. And now we look at the different stakeholders and see which parameters are important. For TSO, they need to know if the current grid code is valid, and also know which parameters are important for the grid code compliance. Probably people will think, okay, why do we need to inject the current after AC fault? And this is actually because that if we look at the synchronous generator domain system, dominating the system, if there is a AC fault happens, the synchronous generator will inherently react to a fault through an injection of current upon the fault inception without any delay. So to mimic this synchronous generator characteristics, so we just think maybe after the fault, the converter can also inject the fault current, especially the reactive current, to support the grid side voltage. And here is how we inject the current. And but how much current we should inject and how fast the current we should inject, these are the degrees of the freedom. For example, here is the negative sequence current injection, and when we inject a different negative sequence, how the negative sequence voltage changes. And different colors means different injection levels. For example, we look at the blue dashed black and the solid black line. Here we can see that when we don't inject any reactive current in negative sequence, then the negative sequence voltage will be very high. And when we inject some, then the negative sequence voltage will decrease. And here we also see some nonlinear effect. For example, here actually the solid black line is injecting higher negative sequence reactive current, but here it doesn't really react to a lower negative sequence voltage. So there is some nonlinear. And TSOs need to specify the characteristics, timing, and the accuracy of the fast fault current. And only this, the converter can make sure that they are really supporting the gray side current, gray side voltage. What we need to know, that which control parameters are important for the gray side current injection, right? And here, as we say that the speed of the full current injection will be very important, and also the grid code actually specified that the rise time of the injected current should be lower than at least 20 to 30 milliseconds. So here we use the rise time of the reactive current injection as the output to find out which parameters are more important. And I just present the results of the positive sequence. Here is showing in the same way of the other results, like the X is the mean value of elementary effects, Y is the standard deviation. And here we can see the square, which are the FCI fault current injection related parameters, having the highest mean value, which means they are having the highest impact on the fault current injection, especially the rise time. Except that the PIR also has impact, and which means PIL, fluid current injection are the most critical parameters for the fluid current injection. So the TSOs need to have access to these parameters and to make sure that the converter actually injected enough current during the AC fault to support the gray side voltage. And the less influential parameters are the energy balancing dominated the system, dominated energy balancing related parameters are shown in these stars. And there are also interaction exist among the PIL and the deadband and also this fluid current injection because they have relatively high standard deviation. And probably we cannot really see clear from just this figure. So let's look at the other figure. Here is a wiring plot, and basically it's because we changed the different parameters from one level to the other level, and this plot is to put all the results in a same figure, but organized with the difference of KFI from 1 to 6. And we can say when we increase the droop of the fluid current injection, the rise time of positive sequence is decreasing, and it's decreasing very significantly. And also, but when it's injecting too fast, for example, when the droop is larger than 4, the change is less significant, which means this impact has some nonlinear effects, and the same on the negative sequence injection. And from this figure, we can go to the time domain waveform. For example, here we choose the the current injection droop as 4. Then we can see the injected current rise time are less than 10 milliseconds. But if we decrease the fluid current injection droop, then the rise time will be among 20 milliseconds or 12 milliseconds. So basically, this tells us if TSOs found that some converters injection are not really complying with the grid codes, they know that must be the droop setting having some problems. So they need to tune the droop setting. And for the vendors, they need to make sure the converter design safe under the fault scenario and also communicate the model transparency with their customers. And for the converter safety, the key consideration is the internal stress on the converter during the AC fault. And here, to represent the stress, we actually use the maximum current of the arm current. It's basically we constantly measure the arm current, and then we choose the maximum current point after the fault. And then under our different simulations, we record this maximum current, and then we will find which parameter change will lead to the most maximum current change. And here is the sensitivity analysis. And one interesting thing we find is that we thought for the internal current, for the internal MMC characteristics, probably the energy balancing will play the most important role, but actually the outer loop fluid current injection parameters are more important than the internal energy balancing. So which means the vendor also needs to make sure that when they change the current injection under the settings that the TSO gave them, they have to make sure the converter are still safe under different fault scenarios. And the second critical parameter are the PIL, and which is also surprising, which means that the PIL parameters also plays a role on the internal arm stress. And under different system conditions, as we know that if the system is too weak, then the PIL cannot really tune very fast, otherwise the system will be unstable. So that means under different system, PIL's parameters might be tuned differently, so it might also cause different stress on the MMC arms. So the vendor, when they design the converters, they also need to consider this point. And the third one is just the energy balancing related parameters, which we all know. But one thing surprising is the horizontal balancing energy parameter doesn't have critical impacts on the arm current maximum. And the other part is for the model transparency, because usually to protect their intellectual property, they usually provide the black box model to TSOs to their customers, and this will increase the complexity to understand the control response to different scenarios. And we want to say that if we can have a standards that which part of the model should be open to the customers, which part can be closed, and under different research perspective, then this will make the communication between the vendors and the customers easier, and also it can reduce a lot of engineer hours, because we already know the parameter, which parameter is important. Then the understanding will be more straightforward. And here I give an example of two different systems. One is MC has a close bisynchronous generator. The other is when MC doesn't have a close bisynchronous generator. And when there is an AC fault happens, and when we change the strengths of the system, and the PIL has to be tuned differently. For example, here is when the system 1 short circuit ratio equal to 5, but the system 2 short circuit ratio equal to 8. They are relatively strong system, and we can see that the proportional and the integral gain of the PIL can be chosen under this large domain. But when we decrease the short circuit ratio of both systems to 1 to 3 and 2 to 6, then this domain, that's the parameter can be chosen, are decreased. And make it even weaker, then we can see that the proportional gain of the PIL in these two systems are even smaller, which means to make sure the converter can work under different system scenarios, the PIL parameters has to be open to the TSOs. And when the system change to make sure the system still stable and still robust, they can actually tune the PIL. And we did the similar research to different parameters, and we actually found that for the AC fault analysis, and we think the PIL, internal energy control, especially the total energy control, fault current injection, and the outer loops, these parameters need to be open to the customers, but we just need the key parameters. We don't really need to know how the control blocks are implemented. So it's basically still protecting the intellectual property partially. And for the control engineers, we just want to know the how we design the control better. And here I choose the DC voltage regulation as an example to explain how this method can be used. And for the MC system, one important part is the total energy control. And for the total energy control, we can use both AC side power and DC side power to regulate the total energies. For example, if we open this tap, then we are using the AC side power to maintain the total energy installed in the MC. If we open this tap, we are using the DC side power to do the maintain. And because when we're using different tap, and this will create some interaction between AC and DC side, especially when we're just using partially AC side power and partially DC side power to do the MC total energy balancing. And so that means the AC side related fault scenario or the AC side fault current injection might also have some impacts on the DC side voltage regulation. And using the sensitive analysis, we can show very clear and even in different time scales. And here, basically, I measure the DC voltage after the fault happens every 10 milliseconds. I will record the DC voltage once, and every 10 milliseconds, I will calculate the elementary effects once. Here, then we can see after the fault from 0.3 to 0.5 seconds, and how the elementary effects impact, and this will tell us which parameters will have impacts under which time scales. And here we can see the purple star is the DC voltage, and it has impacts immediately after the fault. But the AC side fault current injection also have impacts, although its impacts are a little bit slower. And here represents the impacts of the energy control, the total energy control. It also have some impacts, but only the impact happened during the transient. So this basically tells us, even though we are looking at the DC side voltage regulation, the control engineer cannot overlook the AC side fault injection. And for the protection engineer, we basically care about if the fault detection method is still working under the converter domain system. And here I use the distance protection as a research object. And usually when we analyze the impact of the injected current to the distance protection algorithm, we basically only think about this parasitic term, and when this phase angle difference is 0, then the injected current will cause the impedance shift along the R-axis, and when this angle is not 0, then impedance will shifting with the angle of this this value. But this can only tell us impact chancing, and it's not really accurate. So it's not really easy to evaluate the protection results just using this current injection. So here we are using a different method. We measure the distance between the trajectory and to the action zone. And here, because the fault is zone 1, so we measure the distance between the trajectory to the action zone 1. And when the distance is larger than 0, then that means the trajectory is still outside. And when it's 0, it means it gets inside. And then if it's negative, that means the trajectory enters the zone and stay in the zone stably. And this can basically evaluate the overreach, underreach, and also the response time of the distance protection. Here, still look at two different systems. One has the support of close-by synchronous generator, and I used the two different outputs. One is the response time of the distance protection. Actually, is the when the distance protection trajectory enters the zone. Here we record the time, and also after it enters the zone, the distance between this trajectory to the zone. If this distance is large, that means it's pretty much inside the zone, that's more stable. And if it's close to the edge, especially when there is some points that it enters the edge and enters out, then the results is not really stable, then the distance protection cannot detect fault. So this parameter is also very important to look at. And then we did one sensitivity analysis, and we found that here is the upper part is the mean value, the lower part is standard deviation. We just look at very broadly, yeah, and we will see that in system 2, these bars are much higher, which means only one MMC doesn't have a close by synchronous generator or close by AC grid system, AC grid, then the impact will be very large. And if there is still a close by synchronous generator, then the impact are not really significant, but we can still say that when the system is weaker, the synchronous generator weaker, then the impact of MMC on the protection results will be more significant. So the impact on the protection actually very relates to the grid system, the system strength, and the network. So we need to make sure, we need to analyze under which system that we need to make some fundamental changes on the protection or the control. So we did a very complicated research, and I'm not going to really show how I did it, but I'll just show the results. And basically, these are the parameters. For example, the first row is the parameter pair of the fault current injection droop and the limitation of the current injection. And here is the deadband and the PRL, and here is the total energy control ratio and the proportional gain of total energy. And this part of the results is when it has a synchronous generator close by. This part of the results, it doesn't have a synchronous close by. And we also change the system strength from weak to strong, from left to right. And we can see that when the system and this domain, it shows that we have to make sure the parameter to be tuned in this domain, then the impact on the protection will be minimal. And by comparing the area of the domain, we will actually know that how much impact of the control parameter have. For example, when the system is much weak, here when the stress ratio is only 2, then this domain is the smallest. And when it's getting stronger, this domain can be also stronger. That means we can choose, we have more freedom on choosing the parameters. And when there is no close by synchronous generator, we can see that under a weak system, there's still some parameters we can choose to make sure the protection works fine. But when it is a little bit stronger here, we can even not find any parameters to make sure the protection works fine. And this has very different results compared to this one. So yeah, under this research, it can tell us when we go to a system like this, it doesn't have any synchronous generator close by the MC, and for example, the power system is fully MC dominated or converter dominated, then the original protection algorithm will never work, and we need to make some fundamental changes. But right now, we are still in this stage, so we just need to make sure that parameters are tuned properly so the protection can still work. Now with this, I can basically close my presentation. So I use the synchronous generator and look at for different stakeholders, which parameters are important. And this can basically help them in different ways. For example, for the TSOs, it can detect the critical parameters for the critical compliance and because the different system strengths and system network also have impacts on the critical compliance, and this can basically make the analysis more straightforward. And for the TSOs, they can use this method to provide some operational guideline. And in the future, when the grid changes, they know which parameter to change, at least which parameter domain they need to choose. For the vendors, they can get standard control blocks, which means they can choose which part should be open to the customer, which part can be closed. And this can streamline the product integration for the control engineers. They can understand better about the control system and tune the control parameters more efficiently, and align the control function with more dynamic systems. For the protection engineers, using this method, we can know which parameters are more important. So we can simplify the models for the protection test and design in the large system, and use this data, we can dynamically set the protection thresholds, and also try to collaborate with the control teams to align the protective device settings, and it can improve the protection in a more efficient way. Yeah, this is the presentation, and thanks for your attention. I hope you get some information from this, and thanks.
Thank you very much, Xiaoxiao. So now we have 10, 11 minutes for questions and answers. So thanks a lot for providing the questions in the Q&A part. Please still continue to write the questions if you have more. There's a few questions on grid forming versus grid following. So as Xiaoxiao mentioned, this work is mainly on grid following converters. But Xiaoxiao, maybe you can respond to these questions. So first of all, how will the analysis change if we move from grid following converters towards grid forming converters? What will the key findings be? And what may be the differences when we move towards grid forming?
Okay. For the grid following and grid forming, if we just look at this analysis, it's basically changing the parameters and to see the output. For different control strategies, especially for grid forming, that means we are choosing different parameters to do the analysis. And from the control response perspective, actually, even though we say that under the AC side fault, we still expect the grid forming to work in a voltage source way that we can control the grid side voltage and the frequency of the grid. But when the converter is stimulated, is saturated, so it's actually still working in a current injection way. So do they have a big difference? I would say yes, they have when the converter is not saturated. But after they are saturated, they basically are just the current source injecting reactive current to the grid. So yeah, but using the sensitivity analysis, we can find which parameters are most important when the converter is not saturated, and under which kind of scenario the converter is easier to be saturated, and then which parameters will be better for the grid side voltage control.
Okay, thank you.
Yeah.
So there's also a few questions about the methodology. So yeah, so there's a discussion about how computationally feasible this method is. So if we have so many parameters, especially for lots of power electronic controls, TSO level study, how computationally feasible is this? And then there's also a kind of related question about if we can make generic, no, sorry, if we can cover all of the relevant combinations of parameters with this method, because with this method, you choose selected combinations of parameters. Can we ensure we cover all of the relevant combinations with this method?
This method is basically based on simulation. So each time we basically just simulate one type of method, and for the possible parameters, we first will have a basic research and to know that which parameters might have impacts on the AC fault analysis, and we choose all of the possible parameters to do the analysis, and select the parameter domain and divide the parameter in different levels. And if we want to do every scenario, every parameter domain, every parameter combinations, there will be a lot of simulation. So we use the way which is called Morris screen, or we can also use Monte Carlo to randomly choose some parameter in the parameter domain and to reduce the simulation number. So this method is needs a lot of computation workload, yes, but we can use Monte Carlo or Morris screen to reduce the workload. And for the generality, because each simulation we can just use one model. So what I did is like I use different control method and different models, and I implement the sensitivity analysis in different control models. And I mean, even though they have different implementations, they have the same philosophy, and the parameter domain, the parameter definition actually are defined almost the same way. So we will still find that the most critical parameters among different models are the same. And also, we also need to consider that different fault scenario, different pre-fault operation point and operation mode. So for each different scenario, I will do different sensitivity analysis and still find that they got the same results. So I would say, it needs some work but it can get the result. It gets basically worse the workload.
And there's some maybe you can quickly answer some related questions here. Is it specific to MMCs? Is it useful for other inverter-based resources for analysis of other inverter-based resources? And also, yeah, can we make generic conclusions? Are the results you present for all converters, all MMCs, or is this how system specific is this?
Yeah, this method is it can be used to other converters and even other research objectives, as long as you can define the input parameter, output parameter, and also calculate the elementary effects. And it's not only for the high voltage level MMC converter. It can also be used for the results I got is also applicable for the medium voltage or the low voltage converters.
Okay, good.
Mm-hmm.
Yeah, so there are some questions more relating to sort of network protection and these things. So it's not necessarily, I'd say, the focus of this presentation, but maybe we can also have a quick discussion. So when short circuit level is low, how can one ensure the protection scheme still works?
Let me go to that slide. Here, right? So here we use different parameter, different output parameter to define if the protection is working. For example, here maximum D is like we calculate the distance between the trajectory and the zone after it enters the zone, and we make sure that the distance between the trajectory zone is large enough, and optimal the results among the maximum points. And the minimum time is like we make sure the trajectory enters the zone as fast as possible. Also, we optimal the parameter among the minimum time points. And the area port is like we make sure the faulted trajectory enters the zone, but the healthy trajectory will not really enter the zone, which will make sure the selection of the protection. Basically, we need to make sure all these parameters or all these outputs will comply with the requirements and constraints. Then we choose the parameter under the constraints, and these are the results we found. So when there is a synchronous generator close to the MMC, the impact of the MMC is large, but the synchronous generator is still playing a role. That is why we can still find some doable MMC parameter to make sure the protection is working. But for this one, when the grid is weaker, that means this part of the remote synchronous generator or remote grid is weaker. Then the MC can find some parameter that the protection can still work. But when the remote grid is stronger, we cannot really find the parameter, which is because that. Let me go to this part. Yeah, because the injected current or the calculated apparent impedance is impacted by this parasitic term, and I2 is the remote grade injection, and the I1 is the local injection. And when the remote injection is very large, then the parasitic term will be also very large. Then the apparent impedance calculated will be far away from the actual photoimpedance. Then it will not really get inside the protection zone. That's why when this part of the grid is stronger, then it will cause negative effects on the distance protection. So that's why we see that in this system, when the system is weak, the MMC can actually find the parameters to make the protection work.
Okay.
Yeah.
Thanks a lot, Xiaoxiao. So yeah, thanks everyone for the questions. For the ones that we didn't manage to answer, we'll try and answer them later and distribute this. So yeah, I think it's time to wrap up. So thanks very much for everyone for joining. This is the latest webinar in a series of Etch Energy Transmission Competence Hub webinars. Please keep an eye out for more webinars in the future. We'll be having a few more in the following year, in the rest of the year. And for those based in Belgium, we will organise a second annual Belgian Energy Transition Workshop on 16th September. So please check the Etch website for that. In general, please follow our LinkedIn and keep checking our website for future events. So thanks very much for joining, and see you at the next webinar. Thank you.
Thank you.